Hello everyone, welcome back to my channel. In today's video, we will discuss about power in forced vibration and resonance, sharpness of resonance, quality factor and the relation between quality factor with logarithmic decrement, relaxation time and also damping. Before starting the class, if you have not still subscribed the channel, then do subscribe the channel, and if you like this video, then share with others. If you want to join my online classes, online theory classes as well as online numerical problem solving classes of MACOT BTech Physics syllabus, then you can contact me through the contact number given in the screen, or you can also follow my Instagram and Facebook page as given in the background of my screen. So without wasting the time, let us start the class. First of all, we will discuss about power in forced vibration. Now in my previous lecture, I have discussed about the expression for displacement in case of forced vibration, which is equals to x equals to f into cos of omega t minus phi divided by k minus omega square m whole square plus omega square b square whole to the power half. This is the expression for displacement in case of forced vibration except the damping part. So we take as equation number 1, or we can write x equals to f into cos of omega t minus phi whole divided by, we take common omega and in bracket it would be k by omega minus omega square m whole square plus b square whole to the power half, which we can write as equals to f into cos of omega t minus phi divided by omega into capital Z, where Z is equals to k by omega minus omega square m whole square plus b square whole to the power half, which is called mechanical impedance. So Z is called mechanical impedance. So x is equals to f into cos of omega t minus phi divided by omega into z. So this is the expression for displacement in terms of mechanical impedance. Suppose f cos omega t be the external periodic driving force or external force that is acting on the oscillatory system in case of forced vibration, then the instantaneous rate of work done by the driving force in steady state, or which is called the power. The power is given by P equals to external driving force f cos of omega t into instantaneous velocity, that is dx dt. So this is the expression for x. So dx dt would be f cos omega t into dx dt would be, if you differentiate the equation 2 with respect to t, it would be f into minus omega sine of omega t minus phi divided by omega into z, or it would be minus f square by z cos of omega t in bracket sine of omega t cos phi minus cos omega t sin phi. So here omega cancels out. So finally it would be minus of f square by z into, in bracket it would be sin omega t cos phi minus cos square omega t sin phi, or if we take half common, then f square by 2z in bracket it would be 2 sin omega t cos omega t, means sin of 2 omega t cos phi minus, after taking half common, it would be 2 cos square omega t, that means 1 plus cos 2 omega t into sin phi. So this is the expression for power. Now if you want to calculate the average power, that is average power or P bar or this one. So both are called average power. So if you want to calculate the average power, then average power would be integration of p dt divided by integration of dt limit 0 to t, both the cases, or it would be minus f square by 2z into cos phi integration of 0 to t sin 2 omega t plus f square by 2z into sin phi into integration of 0 to t 1 plus cos 2 omega t dt, here also dt, whole divided by capital T, or t bar would be 1 by t into minus f square by 2z cos phi. After integration it would be 1 by 2 omega into cosine of 2 omega t, limit would be 0 to t, plus f square by 2z sin phi into t plus 1 by 2 omega sin of 2 omega t, limit 0 to t. Now after putting the limit, this term would be 0, and similarly this term will also be 0. So finally we get p bar or average power, that is 1 by t into f square by 2z sin phi into capital T. T cancels out, that is f square by 2z into sine of phi. So this is the expression for average power. So we take it as equation 3. Now to find out the value of sin phi. In my previous video where I have calculated the general solution for forced vibration, I have shown that b sin phi, which I have taken as 2a omega. So in my previous class of forced vibration, I have shown or I have taken that b sin phi equals to 2a omega. So you can go there and check it if you have any doubt. I will also provide the link of the previous video in the description section of this video. So b sin phi equals to 2a omega, or where b is equals to omega 0 square minus omega square the square plus 2a omega whole square to the power half, which is equals to k by m minus omega square whole square plus 2a omega whole square to the power half. Now we take omega square by m square common, then here we get omega square by m square common, in bracket it would be k by omega minus omega m whole square plus b square to the power half, or it would be omega by m into k by omega minus omega m whole square plus b square to the power half. This expression which I have taken as Z mechanical impedance, so B becomes omega Z by M. So B sin phi equals to 2 omega, so we got B, so we put there, we will get B sin phi equals to 2a omega, or B into or omega Z into sin phi by M equals to 2a omega, or sin phi equals to 2a omega m by omega z. Omega cancels out, equals to 2a m by z. Again, in case of solution of the differential equation of forced vibration in my previous lecture, I have taken as B by M equals to 2A. So, we put the value here, B by M equals to 2A. So, sin phi becomes B by Z. Now, we put the value of sin phi in equation 3. So, we get average power equals to f square by 2z into sin phi. So, we got sin phi equals to B by Z. So, this value is B by Z. We get f square B divided by 2z square. So, this is the average power. So, this is the average power in case of forced vibration. Now, at resonance, omega equals to omega naught, or Z equals to their mechanical impedance is under root of k by omega minus omega m whole square plus b square. So, at resonance omega equals to omega naught, that means this value, bracketed value, becomes 0. So, Z becomes, at resonance omega equals to omega naught, Z becomes equals to B. So, the average power at resonance, that is P bar resonance, becomes f square B by 2B square, or equals to f square by 2B. So, this is the average power at resonance supplied to the driven system, P bar resonance, that is equals to f square by 2B, where B is called the damping coefficient. So, the average power at resonance depends inversely on the damping factor or damping coefficient. Next, we will discuss about one term that is called sharpness of resonance. What we discussed previously, that so in case of forced vibration, suppose f cos omega t is the external driving force, and that is acting on the oscillating system. Then the average power P bar versus the frequency graph would be like this figure. So, along y-axis average power is plotted, along the x-axis frequencies of the driving force has been plotted. So, for here we consider two cases. This is case 1 and this one is case 2. We know that at resonance P bar, or the average power at resonance become P bar max, which is equals to f square by 2b. So, it is inversely proportional to the damping coefficient B. So, now we have considered two cases. Case 1 where B is very low, and case 2 where B is very high. So, whenever the damping factor is very low, then the average power maxima value would be very high. That means the graph would be very much sharp and it will have a high P bar max value. So, in case 1 that B value or the damping coefficient is less compared to the case 2. So, case 1 B value is less. So, P max bar is very high. So, for less damping, the average power for at resonance would be very much high. Similarly, in case 2, damping factor is or damping coefficient is very high, so that P bar max value would be very low. That means at very low B value, that is very low damping case or lower damping case, the curve acquires a very high P bar value. That means sharpness of resonance is very high. Similarly, for large damping value, that is large value of B, the graph is very much broad. That means resonance here is very much broad or flat. So, here you can see that at resonance, that is at omega equals to omega 0, the peak values of these graphs are these 2 points. Whenever you are departing from the resonance frequency, the average power decreases very sharply. So, the sharpness of resonance is the rapidity with which the average power diminishes as the frequency omega departs from the resonance frequency omega 0. Next, we will discuss about quality factor, which is denoted as Q. Now quality factor is a measure of sharpness of resonance. Now if we plot the ratio of average power to the power at resonance versus frequency of the driving force as a graph, then the graph will look like this figure. Here we have plotted along y axis p bar by p bar resonance and along x axis frequency. So here are two damping cases. This is case 1 and this is case 2. So case 1 is for low damping and case 2 is for very high damping. From this figure we can see that there are two frequencies which we name as omega 1 and omega 2. At these two frequencies, the ratio of p bar by p bar resonance, that means ratio of power, average power to the power at resonance would be half. So, or in other words, p bar would be the average power would be half of the power at resonance. These two frequencies omega 1 and omega 2 are called half power frequencies. That means at omega 1 and omega 2 frequency, the average power would be half of the power at resonance, that is half of the power at average power at resonance. Or we define quality factor as Q equals to resonance frequency divided by difference between half power frequency, that is omega 2 minus omega 1. So this is called the quality factor of resonance or sharpness of resonance. Now we have proved that average power is f square b by 2z square and also average power at resonance is f square by 2b. So according to the condition, p bar equals to half of p bar resonance or f square b by 2z square equals to f square by 2b. 2 cancels out. So according to the condition, p bar equals to half of p bar resonance, or if we put the value here, f square b by 2z square equals to half of f square by 2b. Half of cancels out, we get f square cancels out and we get z square equals to 2b square, or we put the value of z as k by omega minus omega m whole square plus b square, which is equals to 2b square, or k by omega minus omega m whole square equals to b square, or we get k by omega, or k by omega minus omega m would be plus minus b. So for when omega equals to omega 1, it would be, we take k by omega 1 minus omega 1 m equals to plus b, and similarly when omega equals to omega 2, it would be k by omega 2 minus omega 2 m equals to minus b. If we add these two, we will get k into 1 by omega 1 plus 1 by omega 2 plus omega 1 plus omega 2 into m, that would be 0, or k into omega 1 plus omega 2 divided by omega 1 omega 2 plus, here it will be minus, equals to omega 1 plus omega 2 into m, or we get k equals to omega 1 omega 2 into m. Now we put the value of k in either of these cases. Right, let we put the value of k here. So we get, it is k by omega 1 minus omega 1 m, that means omega 1 omega 2 m by omega 1 minus omega 1 m would be plus b, or omega 1 cancels out, omega 2 minus omega 1, that becomes equals to b by m. Again, so in my previous video of force vibration, we have taken b by m equals to 2a. So omega 2 minus omega 1 becomes equals to 2a. So if we plot if we put the value of omega 2 minus omega 1 in quality factor, it would be omega 0 divided by omega 2 minus omega 1, that is equals to omega 0 by 2a. So quality factor is omega 0 by 2 into a. So this is the expression for quality factor in case of forced vibration. So in this graph, this is omega 1, where p bar divided by p bar resonance would be half, and similarly this would be omega 2. So quality factor would be omega 0. This is the peak value at omega, that means omega at omega 0, that is the peak value of p bar by p bar resonance. So omega 0 quality factor would be omega 0 divided by this omega 2 minus omega 1. So from this graph, quality factor can be explained. Next we will discuss about relation between logarithmic decrement and quality factor. Logarithmic decrement I have also discussed in my previous videos. This question came in 2020 as 3 marks question, that is explain the term logarithmic decrement and quality factor of damped oscillatory system. How are they related? So both quality factor, what is quality factor, and the logarithmic decrement I have discussed. So now we will derive their relation. Now to derive the logarithmic decrement, which I have also derived or discussed in my previous video, amplitude of the displacement part for damped vibration is a e to the power of minus at. Now decrement is defined as ratio of two successive maximum amplitude. And suppose two successive maximum amplitude can happen after a time interval or time period of t prime. According to the definition of decrement, it would be a e to the power minus at divided by a e to the power of minus a into t plus t prime. So it would be simply e to the power of a t prime, or LND, which is called the logarithmic decrement delta, that becomes equals to a into t prime, which I have already discussed in my previous videos. So also I have discussed the what is relaxation time in my previous videos. So relaxation time we obtained as tau equals to 1 by a. So tau equals to 1 by a, which I have already discussed in my previous lectures. So delta or logarithmic decrement, which is equals to a t prime, that means t prime divided by tau. So delta becomes equals to t prime by tau. So which is the relation between logarithmic decrement and relaxation time. So this is the relation between log decrement and relaxation time. Next we will derive the relation between quality factor and log decrement. Quality factor is omega 0 divided by 2a. So which is equals to 2 pi by t prime divided by, where omega 0 equals to 2 pi by t prime, and 2a we can write it as in the form of delta, that is log decrement. So we can write it as 2 into delta by tau, delta by t prime. So t prime cancel out, 2 cancels out, and t prime cancels out. So it will be simply pi by delta, or q quality factor would be pi divided by delta. So this is the relation between quality factor and log decrement. Next we will discuss about relation between quality factor and damping. Now Q factor is used to determine the qualitative behavior of damped oscillator. In case of forced vibration, the damping part is also present. So the quality factor is used to determine the qualitative behavior of the damped oscillator. Now in case of under damping case, quality factor is greater than half. So what we know in case of under damped vibration, that is first of all, quality factor is greater than half. A poor quality factor just above half will produce 1 or 2 oscillations, and it will gradually dies out with time. That means quality factor in case of underdamped vibration, quality factor is greater than half, and the system will oscillate and the motion of the system will be oscillatory, but it will oscillate very less and gradually it will die away. So, in case of overdamped condition, quality factor is less than half, and also we know that in case of overdamped condition, the system becomes non-oscillatory in nature. That means the motion of the system is non-oscillatory, and when the system is shifted from the rest position or the equilibrium position or steady state position, then it will come to the position of rest very slowly and with a exponential decay. And thirdly, in case of critically damped case, quality factor is half. And here also the system is non-oscillatory in nature, and system when shifted from its equilibrium position, it will come back or return to its equilibrium position as fast as possible. So, as quick as possible it will return to its equilibrium position. So, this is the relation between quality factor Q and damping. So, this is the end of today's class. See you in the next class. Till then, bye.